Okay, well, I'm going to talk about augmenting intelligence by good old-fashioned natural intelligence, essentially how to teach people so they'll be smarter, particularly in science and engineering. And what I mean by smarter is really looking at how they think like, or what we really look carefully at is how they make decisions like experts in the field, and how we can more effectively teach people to do that. Whether it's, I focus on undergraduates at universities, but the ideas apply if you're at a company and you're worrying about training programs, et cetera. This is ultimately what almost all of our education is really aimed at. So, but to start out though, I'll sort of take a step back and look and say something about kind of how knowledge evolves in society. I mean, you start out with everybody has an opinion, and basically it's kind of everybody's treated or feels like they're an expert with all of these things equally valid. And then society progresses to stage 2, which is where you formulate opinions into testable hypotheses, and you start doing experiments that separates out which of all these opinions is actually right and which are wrong, and at the same time out of that grows expertise, the realization that people who know certain things are right a lot more often than those who don't know those things. And if you sort of look at how this happens in different fields, looking at physics, well, physics started out, the study of physics started out the first time some pre-human creature tried to throw a rock at something. But then it reached stage 2 with Galileo and the idea of dropping rocks off of the Leaning Tower of Pisa to really test these ideas. And so that was back in about 1600 for physics. Biology and medicine, it was a messier subject. There was more vested interest in the status quo, so it took a couple hundred years more. But it, reached the point with Pasteur and his laboratory studies of germs, etc. Education is still back in stage 1, I'm afraid. Everybody's an expert on education. But, that's part of the reason all these fads come and go and so on. But hopefully, very optimistically, maybe, in another 5 or 10 years, we'll start to seriously move into this stage 2 of real empirically driven science. And I'm going to talk about and give you an example of some things that me and others like me in science engineering education at the undergraduate level are sort of pushing these ideas forward and what we're able to achieve doing that. And so work like I do is really combines the work in science, undergraduate science classrooms, testing different ways of teaching and comparing the results, primarily in terms of what I said before, giving students, simple situations and see if they can make decisions like a recognized expert in the field, a physicist or an engineer would do. And then we combine that with the work from cognitive psychology, telling us about principles of learning and the nature of expertise and its acquisition. And those come together in developing and testing really better teaching methods and these turning students into more effectively turning them into experts as a result of their courses. So in this talk, I'm going to start by first talking about, what is thinking like an expert? What do we know about that? What do we know about how it developed? And then show you how that can be implemented in the university classroom, and then show you some data from when we do implement that, how the learning compares with more traditional approaches. And then at the end, I'll give you, since everybody loves technology, I'll give you a quick example of some basic research on learning where we're taking the advantages of some technology to make possible things people haven't been able to study before. Now, I won't get into all the details of actually how you implement these properly in a classroom. You have to take my word for it. There is some expertise involved here. If you really want to know all that, talk to me later and I'll give you references. So, cognitive psychologists have studied a lot about expertise, looking across many different fields, and they find there's a few basic elements which are common across all fields of what makes up expertise, and there's also a very consistent pattern about how expertise is developed. And so, starting with what are the components of expertise, well, the first one everyone would guess, experts have a lot of factual knowledge about their subject. But the other two aren't nearly as obvious. It turns out that experts in any particular field, they have not only knowledge, but they have, unique to that field, a very special way of organizing all of that knowledge. And this mental organizational framework allows them to be very efficient and effective at getting the information they need to solve a particular problem. So these organizational frameworks, they involve organizing things about complex patterns and relationships that one looks for. And if you think about what a science or an engineering concept is, it's really just the way that scientists in a particular field took a whole bunch of different pieces of information and saw a way they could organize that all together so that then when they're faced with a new problem, they could very quickly decide if that whole body of information was going to be useful or not useful, and they could set it aside and look at other things. Now, the third aspect of expertise is really the ability to monitor one's own thinking and learning, at least in the subject. And so, as an expert working in some particular field, they have a little voice in their back of their mind saying, do I really understand this? Is this a sensible way to be solving this problem? And it turns out they get another little voice that can actually answer them and guide, and so they change what they're doing accordingly. Now, the research also shows that all of these things are fundamentally new ways of thinking. No one naturally comes to have expertise in any subject, although there's lots of myths about this. The research says it's just not true. That everyone requires many hours of very intense practice to develop this expertise. In fact, to reach a high level, it's many thousands of hours. And I think it's becoming increasingly clear in recent years that this is a basic biological limit. That really, as a result of this certain kind of intense practice, the brain is actually rewiring itself. And it's really in this rewired brain that the expertise lies, but it takes a lot of time and effort to get the brain to make enough changes. And so it's very analogous to, if I want to build up a muscle here, I got to use that muscle strenuously, and I got to do that over and over again. And the body sort of reluctantly agree, okay, you're going to use it that much, I'm going to make it stronger. It turns out it does much the same thing with the brain. So now I said it takes many hours of intense practice, but these studies have also shown that it's a very special kind of practice that's required. And it's got to be things that are very challenging. Again, just like building a muscle, I can lift tiny weights forever and never get any stronger. I've got to do something that's really hard but not impossible. And it's got to use the right muscle. It's got to use the right parts of the brain. It's got to be very explicitly practicing the kind of thinking, decision-making that makes up the expertise that you want the learner to acquire. And on top of that, of course, practicing something isn't any good if you don't know if you're doing it right or not. So there's got to be a process of feedback that as a person practices, they get feedback as to how they can get better, how they can improve, and so on. And then you go through this cycle, and you just, and ultimately they develop more and more. So when I talk about practicing these components of expertise, I want to just give you a little better sense of what I mean by this. Some components of science and engineering expertise that apply quite generally in every field. I'll just list some. Every field has a particular set of concepts and mental models that people use to work in that field, and more importantly, and often overlooked, they have a very sophisticated criteria for recognizing when particular models apply and don't apply to a given context. They also have, very complex pattern recognition systems, if you like, that allow an expert to look at a problem and rather quickly and effectively sort out what's relevant and what's irrelevant to be solving this problem. I'm hoping that all of you are sort of thinking about your life and context and what your work, and recognizing these things map over pretty well to almost all kinds of problem solving. Every area has different, but everybody has quite explicit criteria that they use for when they get an answer or conclusions, or checking if this makes sense, if there could be a better way to do this. And when I'm doing a physics problem, I have one set. Somebody else is doing, working a problem in ecology. They have a completely different set. I don't have any idea what they do, but I know if I go in there, I'll see that they have a set of things by which they evaluate their results. And everybody has very particular specialized ways of representing information. And experts can move fluently between those different representations, and in doing so get new insights that gives them new capabilities for understanding and solving problems. So these are the kind of things that one really needs to build in the practice, thinking and using, if you want people to learn to be an expert. Now, it didn't say anything about knowledge, and of course in most discussions about education, they're all focused on what knowledge are we going to give kids and students, and what topics. And the point is that knowledge is really only useful when it's embedded in these broader areas of expertise that give the learner an idea of when and how to use that knowledge. We have lots and lots of data showing that we can teach people particular knowledge, and then when faced with a problem, they never know how to use that. Okay, so in this context of that's how people need to learn, it's useful to think about, so what does an effective teacher do to make this happen? Well, an effective teacher, they are really very much like the counterpart to a good athletic coach. So I sort of think of a good teacher as a cognitive coach. If you think what a good athletic coach does, they break down whether it's hitting a golf ball or playing tennis, or they break it down into particular skills, and they think of good ways to the learner, the athlete, to practice and become good at those skills, and then put them all together to be successful. So they design good practice tasks that really embody what you want the person to be good at. They provide timely feedback on how to get better, and they motivate people to put in the fundamentally, intense, focused effort that's required to become good at anything. And if you think about it, all of these things really require a high level of content mastery. If you want people to think like an expert scientist or engineer, you've got to know what that thinking's like in order to do any of these tasks, okay? And so, in fact, just as a passing note, I would say this is the fundamental and really ultimately only real justification of the research university, where you have the greatest experts in the forefront scientists and engineers in a field who are also supposed to be teaching people. But it's important to recognize that content mastery, high-level content mastery, is necessary. It's not sufficient. And as I'm about to show you lots of data, we have examples that there's also expertise in how you transfer that content mastery to the students. And that's part of what we study, is how to do that most effectively and then how to figure out how to get lots of university professors to accept and start using these ideas. Okay, so that takes me to how do you apply these basic ideas of learning expertise to a classroom? Okay, so I'll just give you a quick example, picking a great big giant class of 250 students here, and how we can do this, and we've shown we can do this effectively, just using a little bit of technology to, in this case, kind of augment the capabilities of a good instructor. So the example I give you is I'm teaching about basic electricity and voltage to students, and so I start out by giving them a very targeted reading of before class, and I don't expect them to learn the subject from that, but they can learn the basic basic facts and terminology, so I don't have to waste class time being a talking textbook, That should have become obsolete with the invention of the printing press, but in fact it's still hasn't kind of caught up with most university instruction yet, that modern technology. So, okay, so then a brief online quiz so that they're rewarded and check that they've done that, reward them for it. And then rather than class starting with me giving them information, I start with a question or a task. So, for example, in this case, it would be looking at this situation with light bulbs and batteries here, asking them, if I close this switch, what's going to happen to the brightness of that bulb? And every student has a little personal response system, so they push the button on that, and that goes, and the computer records who they are and what choice they made. And I mean, this provides, it's a very simple technology, but it's very effective in a couple ways. One is, as an instructor, I get an immediate view of what the distribution of student knowledge is on that subject, but probably more importantly, it requires the students to commit to an answer at which they're at some level, often graded not at all or very little, but there's some level of accountability, even if nothing else. They know I can go in there, and I will go in there and look and see what they chose and if they did it correct. And that kind of committing to an answer which you're accountable at, even at a very low level, really causes people to focus much more on thinking about the issue and primes them much better to learn from subsequent activities. In this case, the subsequent activities are, before they know anything more, they don't see where everybody voted, then in this big class, every 3 adjacent students is part of a consensus group, and they have to talk to each other, come up with the right answer and the reasons the other answers will be wrong. And while they're doing that discussion, I'm running up and down the aisles, or strolling, listening in on those conversations. So I'm getting little snapshots of what's going on in all those students' brains. And it turns out if it's a room like this, okay, you can only sample the aisles. That still covers 80 or 90% of the thinking students are doing. You'll have a pretty good sense of. And so, okay, then one demonstrates, shows the students results, and I, as an instructor, would lead a follow-up summary in which I review, go over, bring out the aspects of student thinking and reasoning, conceptual models are correct, but more importantly, which ones are incorrect and why they're incorrect. Turns out, this is what useful thing I learned from cognitive psychologists, it's all the learning takes place not when you learn you did something right, it's when you learned you did something wrong and why that was wrong and how to change it, okay? So this is often, again, really skipped over. So often if students get something wrong, the instructor tells them the right answer. No, that doesn't do any good usually. They need to go over why they had the wrong answer and what reasoning they need to change on that. And when you're teaching this way, this also because the students are so heavily engaged, then it generates many more questions as the students refine and test their conceptual models, work to apply them in broader contexts, etc. So how is this getting back to what the point is? How are they practicing thinking like physicists? Well, you think about they're having to decide on a conceptual model of how electricity flows, what things are relevant and irrelevant in that problem to solve it, and they're having to make predictions based on that model, test it against what happens, and they're having to defend it to other students, what the reasoning is, and they're having to listen to other students evaluating their reasoning, learning that all-important way of testing your thinking and the correctness of it and changing it as needed. And they're getting this, again, all-important feedback that can help guide their thinking in a very real-time way, both by looking and seeing what their prediction compared to what happened, but more importantly, their interaction with other students and the feedback they get from them, and the feedback they get from me, the very now highly informed instructor, targeting the particular aspects that they're having difficulty with. Okay, so that's the basic idea. So does it work? Well, I'll show you a few examples. It's an interesting fact of people that this kind of research that we do at the undergraduate level, it's not that widely known. It's done by, people in physics departments or engineering departments necessarily, not in education schools. But the results are much cleaner and more definitive as to what's effective teaching than you can ever get from research at the K-12 level. And that's not because researchers at the K-12 level are stupid, it's just that there are so many other variables that it's much harder, more difficult to do clean research studies. But I'll show you a few examples of the kind of things, particularly good examples, that we get from science and engineering classes at the university. So this one is looking at the topics of force and motion covered in every first year physics course, and then giving students simple real world problem and situation and see if they can apply those concepts like a physicist would to make a prediction of what's going to happen there. And in physics education research, we've developed some rather careful tests that we give students before they take a course and afterwards to see how much they've improved in this, conceptual mastery like a physicist. And in this study, Cal Poly, I particularly like it because they had a bunch of different instructors with a bunch of different sections, relatively small sections. They collected data for a number of years, and they found that these students were a learning gain of a little under 0.3, which means that of the material the students didn't know, they were learning a little less than a third of it as a result of taking this course. Now, keep in mind this was fundamental, essential material covered in this course, but we have data from lots and lots of other introductory physics courses like this showing that that's actually a pretty good result for a traditional lecture taught physics course. Well, it's a relatively good result. In absolute terms, no, there's nothing good about it at all. It should be 100%. Okay, but in this experiment, what they did was they then had all of these sections, all these instructors, switch over to what they call a studio approach, but that's really the sort of thing I talked about in a smaller scale. The students were given carefully developed problems to work through in small groups, members 40 in a class, and the instructor walks around acting as a coach or facilitator, helping them and giving feedback along the way as they work through these problems, which all the sections working the same. So after that, they then go back and give the students these same measurements of pre and post learning, and basically their average just doubles, and all of the instructors, in fact, within the statistical noise, all the instructors are doing about as equally well now. So this is, the thing to recognize here. We have the same people, the same instructors, same personalities. They simply change their teaching methods to be more scientific, and you get dramatically improvements in learning this way. And, this person I like to, I don't know who they are, but, this is a factor of 6 improvement in learning for this particular person, just changing his teaching methods. Shows you how powerful these ideas can be. This is an example from computer science. Beth Simon's someone who worked with me for a year, and then she went back. She's in computer science at UC San Diego. She went back and worked with the other 3 instructors who, the 4 of them teach the core introductory computer science courses there, and implemented what's called peer instruction. It's exactly what I showed you with the electricity example of teaching computer science with these sort of clicker questions and in-group discussions there. And they looked at the drop and failure rates from these courses, and you can see they, across the board, they dropped dramatically. And so now the average is about 1/3 what they had before. Now, if you stop to think about this, UC San Diego is a big place. This means there are hundreds of students every year now who are able to successfully pursue a career in computer science who were being left behind simply because less effective teaching methods were being used. Finally, I want to end with one last example, one I involved with, and that was just learning in the classroom. And so the other studies I showed you were looking at the amount of learning success over an entire term, but that involves what happens in the classroom. It involves studying for exams, homework, etc. This one focused on just the learning that takes place in class. And so we took a big course that had multiple sections of this one, the physics course all the engineering students had to take. We had 2 sections where we measured them to death, and we showed they were exactly identical in attendance and exam performance and all kinds of other things. And then in one of these courses, we had a regular instructor who was somebody who taught this material and this course many times with high student ratings. And so by the standards of University of British Columbia, where it was done, and frankly, the standards of Stanford University, that person is considered a good teacher, well above average. The experimental section was taught by somebody who was a relatively new PhD in physics, so hadn't much experience teaching, but had been trained in my program at these principles and methods for effective teaching. And so the 2 instructors agreed to cover exactly the same set of learning objectives and exactly the same amount of class time. And then they developed an exam that tested the students on those objectives that they gave as a pop quiz to students right after they'd finished going through the 1 week of lectures, started the next class. And it was carefully timed to make sure the students weren't studying for exams or homework outside of class. So how did the two courses perform on this exam? Well, you have to wait to build anticipation. In the experimental class design, it was almost exactly like what I described for the electricity example. It's just in some aspects of this class, they had things were a little more mathematically complicated, so they, instead of all answering with clicker questions, they sometimes had worksheets where students would have to write down things and talk to each other about what the answers were. But otherwise, and I want to emphasize this fact that it's not that a class taught this way doesn't have an instructor talking in it. In fact, they talk quite a bit. But the students are prepared to learn from that talking. The students have been primed for it. It's follow-up response to what students need, not giving them information before they need it and before they know why it's useful. Okay, so here's the results. On this test, random guessing would give you 3, so you have to sort of look at the amount of learning as sort of how far above 3 people are. And I hope I don't, and yeah, I should explain what you're looking at here. This is the score on the test this way, and this is the number of students who got it. So this is the distribution of one class, this is the distribution in the other section. And you can see the white, the section labeled in white, the experimental section, is learning a great deal more than the section in red, and where they're learning almost nothing. And that may seem shocking to you, But if you're somebody like me who started out actually measuring what their students took away from my lectures, you realize, no, that's about what you would have predicted, that it's just human brain doesn't sit through a long lecture and take away much from it. We measured a lot of other things about this. Attendance increased. Engagement, of course, was much higher because people aren't just listening, they're working on problems, etc. So those were examples from classrooms. I could give you 997 plus others, which I won't, but I just make the point that this has been shown similar kinds of benefits across at different levels from first year up to, I guess, I can't think of any actual studies in graduate courses, but I know people using it and with feeling it's working in graduate courses, but certainly all range of undergraduate courses and all science and engineering disciplines. Now, the question always comes up, well, does this apply to other disciplines as well? And my answer is almost certainly yes. You can look at the studies of expertise and the cognitive psychology and see that, they would predict that to be true anywhere. In these other fields, there's a little bit of research in the social science classrooms that show gains, but mostly they just don't test them in the classroom. So I would strongly predict they work, but we don't have data to prove that. Okay, so I'm going to switch gears here to talk a little about I do research in all kinds of different things basic research on learning, but then applications in classroom settings like this, testing different ways of teaching, and we do look at how technology can enhance learning, and I'll give you one example of that. Talked about these PhET simulations at the beginning. They're used 100 million times a year. So this is an example, a circuit construction kit, and it's busy building the circuit here, and so you can see light bulbs light up, little cartoon electrons move around, student can play with this, close the switch, like in that case, and so now you know what actually is the answer to that question, see? And so these things provide pretty unique capabilities for helping students learn about the subject, but we're using them a slightly different way here. We're actually using them as a research tool to explore how people solve problems. And so we have what we call the CCK black box, where it's just exactly what you saw, but we start out in the screen looking like this with a black box and these 4 wires coming out. And the task for the student is, okay, there's a little circuit hidden behind there. You've got to think how to connect things to those wires to figure out what the hidden circuit is. And so, it's a problem they have to solve, and one of the nice things about it is we can make that circuit, we have levels of difficulty, and so no matter how expert the people are in the relevant physics and figuring this out, we can make it hard for them. And so that we can really see how they go about solving what's not a routine exercise they can do automatically, but a real problem that they have to figure out. And so really we're using this as probing general problem-solving strategies. Now, of course, we have to prove that the kind of problem-solving strategies we can see people use and what's effective and ineffective on this applies to a broader range of things. We have some indications that's true. You can talk to me afterwards if you want, but we're in the process of proving that more definitively, but just take my word for it for now. So, but if you think about this kind of general problem-solving strategies, for everything any of us do, we know that's probably the most important thing we want in, coworkers, employees, etc., is good problem solvers. But we don't know how to teach problem solving. The way we teach it is go work out a bunch of problems until you get better at it, right? And in fact, as we study problem solving, we realize it's made up of a bunch of detailed sub-skills, and you really have to find what people are weak at and target those, and that will help you make them better problem solvers. Whereas, go out and become a better problem solver, that's like go out and become a great golfer, It's just an awful lot of little pieces there you can get wrong. And so that's what we're so excited by, is that we can look at this problem and we've been able to clearly identify the different kinds of strategies that people use, the different components of different strategies. And, what do we look for in this is, well, first, what questions do they ask? And what information do they seek to answer those questions? And then how do they interpret and act on this information or evidence that they get, okay? Now, I think if you think about those, that applies to an awful lot of different things, not just finding what's behind little black boxes, right? And so to the extent, it's very hard to get that information from sort of normal technology like a paper and pencil test. Here, because of the nature of the interactive simulation, we can actually track what people do, what they seek, how they act on it. And so it's giving us very exciting results of seeing we really can characterize general strategies. We can see particular weaknesses that hinder people's ability to get to the right answer, and particular beneficial aspects to strategies that make them more effective. And we can identify a lot of different details of their capabilities and weaknesses. And of course, the next thing, like I say, we got to do a little more additional testing. We're pretty far along in showing that this is not just this case, but these things, the same person uses these strategies more broadly. But then we can start, now that we can assess things, we can also start teaching these and really finding where people are weak, teaching them how to fix those weaknesses, and then be able to see that they become better problem solvers. So, and it really wouldn't be possible without using technology in this way. Okay, so with that, I'll finish, and I am actually 3 minutes under, so that's great. There should be plenty of time for questions and discussion here. I'll just say that I think this scientific approach to teaching and learning, science and engineering education, hope I've given you a hint that it really has tremendous opportunities to make students, learners of all kinds, more effective learners, more expert workforce, whatever you want to achieve. We want to get into even creativity. I can talk about that. But and if you want to know more about this, here are some good references. My favorite ones are starting on this. And I'll try and see if they can make my slides available to people who want them. Thank you.